Hi, my name is James Hazard and I'm a doctoral student at Imperial College London. This talk will focus on my work to reduce uncertainty in upper mantle rheology and rates of glacial isostatic adjustment using a Bayesian inverse framework to calibrate experimental parameterisations of anelasticity. The framework has been developed to be applicable anywhere in the world, but I will focus on my work to implement it to determine Antarctic structure in this presentation. Please check out the preprint of this work given by the DOI on the screen and provide presentation feedback via the QR code. My key takeaways are the development of a statistical framework for self-consistent mapping of tomographic data into upper mantle structure, as well as the use of this framework to produce high-resolution 3D models of Antarctic viscosity, lithosphere-asthenosphere boundary depth, and geothermal heat flow, each with quantified uncertainty. Understanding the upper mantle thermomechanical structure in the region of Antarctica is vital for the geodynamics and paleoclimate communities. However, two key issues have historically limited our ability to map this structure with confidence. Firstly, a lack of seismic stations within latitudinal proximity of the Antarctic continent has meant that the upper mantle beneath Antarctica and the surrounding oceans were among the poorest resolved sections of the Earth's interior. This has recently been addressed by the ANT20 model of Lloyd et al. In 2020. Using data collected from around 300 seismic stations over the preceding 15 years, ANT20 is a tomography model offering regional scale resolution south of 60 degrees south. The model offers good data coverage across the continent and in the nearby oceans. See the paper for more details. The shear wave velocity at 150 km depth that you can see on this slide shows evidence of significant lateral heterogeneity over short wavelengths, such as a slow wave speed anomaly located beneath eastern Mary Bird Land, consistent with the presence of several volcanic systems. Secondly, simple scaling relationships have been used to convert seismic data into thermodynamic parameters such as temperature and viscosity. These often fail to account for anelasticity. Our ability to reconcile modelling issues with the conversion of seismic data into upper mantle structure has been revolutionised by the development of experimental parameterisations of anelasticity, such as that of Yamauchi and Take in 2016. By using the full physics relating the strain response of the mantle to a seismic propagation, these models allow us to capture the full range of behaviour affecting shear wave velocity. The importance of parameterising anelasticity can be seen here in a plot of shear wave velocity on the vertical axis against temperature on the horizontal axis. At temperatures approaching the solidus, anelastic effects become particularly important, causing a considerable reduction in velocity associated with the activation of diffusionally accommodated grain boundary sliding. This dramatically reduces the temperatures inferred from a slow velocity anomaly as compared to previous models assuming an elastic approximation. In the parameterisation of Yamauchi and Take, shear wave velocity is a function of the mantle's density and a parameter called the storage compliance. Attenuation is the ratio of a parameter called the loss compliance to the storage compliance. These two parameters make up the complex compliance, which is a description of the frequency-dependent stress-strain response of a material. It essentially describes how squishy the material is and can be measured in the lab using a forced oscillation setup as shown on the right hand side. The complex compliance is a function of temperature, pressure, seismic frequency and a set of anelasticity parameters in the Yamauchi and Take parameterisation. The anelasticity parameters are sevenfold. The shear modulus at reference temperature and pressure and its temperature and pressure derivatives, a reference viscosity, activation energy, activation volume, and the depth dependence of the solidus temperature. Knowledge of the anelasticity parameters allows us to map in a forward sense between seismic shear wave velocity that you can see on the left hand side and interesting thermomechanical parameters including temperature and viscosity, such as the viscosity that you can see on the right hand side of this slide. However, there is significant uncertainty on laboratory estimates of the anelasticity parameters. Here you can see two predictions for Antarctic viscosity from the same tomography model, where I've chosen two plausible anelasticity models based on laboratory estimates of each parameter within the model. The key thing to notice here is that the viscosity output between models differs by multiple orders of magnitude. In addition, the lack of calibration against regional data means that a forward approach fails to reconcile differences in structure arising purely from subjective choices made in the tomographic modelling process, such as regularization, the starting model, and parameterization. The figure at the bottom of the screen shows the viscosity output given the same anelasticity model but two separate tomography models. Again, we see large discrepancies. If we instead presume that the anelasticity parameters are unknown, we can turn this into an inverse problem and solve for the parameters by calibrating the mapping against well-constrained Mantle properties. The main constraint is an oceanic plate cooling temperature model. In addition, we use an adiabatic temperature model, an attenuation model, and a viscosity model. To construct a plate cooling model for Antarctica, we make use of regional water-loaded, sediment-corrected basement depth age data on panel A and heat flow age data on panel B. We find an optimal solution shown in panel C with Mantle potential temperature of 1420 plus or minus 50 degrees centigrade. By binning the shear wave velocities in our seismic model by oceanic age and depth, shown in panel A, we can construct a VS to T mapping, shown in panel B. We use three 25 km depth bins over the ranges 50 to 75 km in blue, 75 to 100 km in purple, and 100 to 125 km in red, to characterize the VS to T relationship at shallow depths. To assess the misfit between data and model for this constraint, the VS measurements shown in panel A will be compared to VS inferred by mapping the plate cooling temperatures into velocities given a chosen anelasticity model. As an additional constraint, a 1420 degrees centigrade isentrope with temperature gradient approximately 0.44 degrees centigrade per kilometre is used to estimate temperatures and hence infer VS between 225 and 400 kilometres. This is shown in panel B. Attenuation measurements taken from the radial attenuation model of Dalton et al. From 2008 are shown in panel C. These will be compared to attenuation inferred from VS. A bulk shear viscosity constraint shown in panel D will be compared to the depth average viscosity inferred from the VS. In designing an inverse framework to model this problem, we wanted to capture the prior knowledge from the literature about the anelasticity parameters. Since we wish to produce 3D, self-consistent maps of Antarctic structure with properly quantified uncertainty, we needed a framework that allows us to naturally propagate uncertainty in the anelasticity model into uncertainty in the model outputs. And this uncertainty should take into account the covariance structure in the model space. This meant that a Bayesian approach was the most logical way to tackle the problem. A set of Gaussian priors were estimated conservatively using a combination of a literature search and statistical modelling, and are displayed on the screen here. Once a suitable set of priors was chosen, a particular type of Markov chain Monte Carlo algorithm was used to run the inversion. The GASWAM procedure has been used elsewhere in the scientific community, and is particularly useful in cases where the parameter space is multidimensional and contains significantly non-diagonal covariance, enabling efficient sampling where it would otherwise be impossible to achieve convergence onto the underlying distribution. The result of the inversion is a set of 200,000 posterior anelasticity models. To assess the off-diagonal covariance structure of the parameter space, we can plot the sampling density of each combination of parameters, shown here. A greater sampling density indicates a more probable combination of parameters. There is evidence of significant off-diagonal covariance in the parameter space. For example, between the parameters regulating the elastic component of the response. There is a very strong trade-off between the reference shear modulus and its temperature gradient. A similar structure is seen between the parameters regulating the anelastic component of the response. For example, a very strong trade-off between the activation energy and reference viscosity indicates that a whole family of models lying along this trade-off are equally probable. To utilize the posterior samples we have generated, we first randomly select 1,000 of these anelasticity models, which are sufficient to characterize the distribution. Each model is a unique combination of the anelasticity parameters. By comparing our sampled posterior models to the data, we can confirm that the algorithm has proceeded as expected. Here you can see the 4 Mantle constraints used in the inversion, and now with the posterior model predictions overlain. Each of the posterior models is then used to propagate Vs into temperature and viscosity, and then we can use means and variances to investigate the size and range of the calculated structures. The first of these outputs is the mean and standard deviation viscosity structure, shown here at 150 km depth. Outside of high viscosity regions, which will be interpreted as elastic lithosphere by GIA models, the uncertainty is approximately an order of magnitude less than predictions generated from forward modelling. This can be explained by A, our use of data to calibrate the models, and B, our natural treatment of the model covariance structure. Looking at the Amundsen sea embayment, we find a steady state viscosity of 10 to the 19.9 plus or minus 0.1 Pascal seconds in the shallow upper mantle. This is over an order of magnitude larger than that predicted by Barletta et al. From satellite GPS. And if physical, this would suggest bedrock topography responds less quickly than expected to ice mass loss, indicating a more unstable West Antarctic ice sheet. However, by accounting for the influence of loading timescale on the apparent viscosity, we find it is possible to reconcile the seismologically and observationally derived viscosity predictions. Please see our paper for more details. The sharp viscosity boundary between east and west follows the transantarctic mountain range and is indicative of the dichotomy between old cratonic lithosphere in the east and the West Antarctic rift system. A large low viscosity anomaly can be seen extended through from the Balleny Islands through to the western side of the Ross embayment. This is consistent with the presence of an active spreading centre at the Macquarie Triple Junction, as well as the recent extensional tectonics along the western margin between the Ross embayment and the transantarctic mountains. The second output of interest here is the laterally varying depth to the 1200 degrees centigrade isotherm, which can be used as a proxy for the lithosphere-asthenosphere boundary depth. We find good agreement between our estimates of mean LAB depth and the volcanic record, and for more details you can see our paper. Thinner than average lithosphere predicted over West Antarctica suggests that faster GIA response times when compared to 1D LAB models. By dividing the continent into a West and East Antarctica according to the divide of drainage systems, we can look at the distribution of LAB depths between each side of the continent. We find spatially averaged LAB depths of 230 plus or minus 40 kilometers beneath East Antarctica and 60 plus or minus 10 kilometers beneath West Antarctica. Finally, our method has been utilized to estimate geothermal heat flow by empirically fitting the calculated temperature depth structure according to the procedure set out by Mackenzie et al. In 2005. We find significantly larger heat flows of around 60 to 100 milliwatts per square meter into the base of the West Antarctica ice sheet, as compared to values of 50 to 60 in the east, except for a local heat flow anomaly in the Gamburtsev Mountains. We believe that the origin of this anomaly is unlikely to be physical and instead due to a crustal thickness anomaly in the seismic model. Over long wavelengths, our results are comparable to the work of Shen et al. In 2020, who compared seismologically derived Antarctic temperature structure to known heat flow in the continental United States. To summarize, we have developed a new statistical framework to self-consistently map tomographic data into high-resolution 3D models of Antarctic viscosity, LAB depth, and geothermal heat flow. These come with quantified uncertainty and are suitable for a range of potential applications. For example, our viscosity and LAB depth can be applied to 3D glacial isostatic adjustment models, where uplift rates are intimately tied to rheological structure. Our high-resolution maps of geothermal heat flow can be used to feed into new ice sheet modelling studies. These inputs should therefore help to improve both the accuracy and uncertainty quantification in projections of future sea level rise.